technical training. So before going to the advanced technical training, let me clear you with the few things. Now we have see for the concrete structures. Here, if you see this syllabus, whatever is shown over here, okay, this is common for this concrete structure syllabus. Whatever given over here, this is common for your gate. Okay, this is applicable for GATE as well as for MPSC, UPSC, and for SSC exams also. Okay, so this is the points. These are the points on which there will be the objective questions for you in these exams, and so that we will cover. Now, what I am going to do today. Today I will tell you in short what is working stress, then limit states. Although we have already seen this in detail. Okay. Then the ultimate load design concept. Then we will move to the design of slabs. Today we will see the design of slabs. As you already know how to design the slabs. Still we will go through PPTs. What is the procedure while designing the slab so that it will recalls you. And in the next lecture, then I will take the MCQ questions, that is objective questions based on this. So the question will be given to you and then the time will be given to you, say 1 minute, 2 minutes, you have to give me the answer. Okay, after that I will tell you the answer with explanation. So in this way we are going to cover each and every bit with their MCQs. Okay, so first of all, if we go through the syllabus, you can see here, this is first working stress method. Okay, so working stress we have already seen. Then limit state, ultimate load design concepts, ultimate load method, then design of beams, slabs, columns, bonds and development lengths, prestressed concrete. I think you have not seen this prestressed concrete, that I will explain you later on. Then analysis of beam sections at transfer and service load. So this is also the part of prestressed concrete. Okay, so all these things we are going to cover over here in these lectures. Okay, so now what I want to say that I will not tell you to take down the notes at each and every point. Whenever you find that this is important, you take those notes. Okay, you take those notes, and if I move further and still some writing is left, then you can tell me, please switch to the last slide so that you can complete the notes. Okay, so now we will start. Okay, so okay, so here now we will start with this. So the methods of RCC design. Okay, so what is the meaning of design? First you should know what is the meaning of analysis and what is the meaning of design. These are two different terminologies. We must know what is the difference between analysis and what is design. Difference between analysis and design. So what is analysis and what is design? I have told you all earlier also. So what is the analysis? Analysis means evaluation. Analysis means, just a minute. What is the meaning of analysis? Evaluation of forces. Okay, so suppose now a box is there. If I draw the box over here, suppose now a box is there. Okay, and it is in motion. Suppose now it is in motion, so the number of forces will act over here. Suppose now its weight is acting downward, this is the weight. Okay, as it is in motion, its acceleration will be here. So acceleration is here, means inertia force will be there. Okay, these types of forces will be acting. So let this force will be F1, its weight is W. So what is the value of this F1? What is the value of this W? Okay, unless and until we evaluate all the forces acting on any member, we can't design that member. So whatever may be the member, it may be beam, slab, column, footing, whatever it may be. Okay. So the evaluation of the forces, finding out the values of those forces, it comes under analysis. That is called as analysis. Okay. And once you find the values, suppose now if you do the analysis and if you have calculated some, suppose F1 is 5 kilonewton, W is 10 kilonewton, then now by taking those values, what you will do, you will calculate the dimension of the box. What is the optimum suitable dimension for that box or for that structure? Okay, basically we calculate the dimension of the structure as well as we take the checks for the permissible stresses. Whatever dimensions we are providing for a certain structure. Okay, so that structure by adopting that dimension, it should be within the permissible limits, and those permissible limits are specified to us by IS 456-2000. Okay, so according to the IS code, we see what is the permissible limits, and if the provided dimension, it may be width, it may be depth, or it may be the third lateral dimension, whatever may be the dimensions, those dimensions should be in the specific range. Okay, it should not exceed its limit. Okay, so providing the dimension. Okay, so providing the dimension, then next is what? Checking for. So I will not write specifically checking, I will write here different checks. Okay, checks as per the specification of IS code. Okay, so checks are different. For slab we take different checks, for beam we take different checks, for column we take different checks. Okay, so in this way the providing the dimension is nothing but design, and evaluation or the calculation of the forces, it comes under the analysis. Okay, so now we will move to the further part. So here you know that what is given, the methods of RCC design. Okay, so these are the methods of RCC design. First is what? Working stress method. Second is ultimate load method, and third is limit state method. Okay, so here in short everything is given in these notes, so we will see over here. I will erase these portions. Okay, so you can see here working stress method. Working stress method, this is also called as the elastic method. Okay. Working stress method, this is also called as the elastic method or modular ratio method or factor of safety method. Okay, so in this working stress method, your design load, it is nothing but it is your working load or service load. Okay, so your design load, it is calculated as your design load, it is your working load, or this is called as service load. Okay, service load means at service whatever load is acting over there, that is your service load. Okay, so you take down these points as these are the important points. So the design stresses are called as the allowable stresses, permissible stresses. These words we have used several times, design stresses. Okay, so the design stresses or the allowable stresses or the permissible stresses, those are calculated as, how those are calculated? It is the characteristic strength of the material divided by factor of safety. Okay, it is calculated as characteristic strength of material divided by factor of safety. So by using this formula, we can calculate the design stresses for the specific materials. Okay. Now see, for M20 concrete, FCK is 20. Okay. and for Fe 250, Fy is your 250. This we already know. What are the grades of cement now? Cement, there is from M5, M10, M15, M20, M25, M30, and then so on. Okay, whatever the mix design we want, we can make the grade. But for steel, Fe 250, then Fe 415, and then Fe 500. These are the grades. Okay, these are the grades of the steel. Okay, this 415 and 500, this gives you the strength. Okay, this gives you the strength. So what is the meaning of this MPa? So 250 MPa means what? It is 250 Newton per mm square. So again, what is the meaning of this 250 Newton per mm square? So it says that for 1 mm square area, it can bear a load of 250 Newton. Okay, that is the meaning of this. Exactly, if you say what is the 250 Newton per mm square, so we can say that for 1 mm square area, it can bear this much of load. So this is 250 Newton per mm square. Similar is the thing with Fe415. Similar to this for Fe500. In case of concrete also same thing is there. MPa, and you always remember this conversion. 1 megapascal, MPa means megapascal, it is equal to 1 Newton per mm square. 1 megapascal is nothing but 1 Newton per mm square. Okay, so in the working stress method, the factor of safety for the beams, for concrete material it is 3, and for steel it is 1.78. Okay, so these are the factor of safety. This is the question which can be asked for the MCQ. Okay, these questions can be asked for MCQ. Okay, and they will give you the various options and you will get confused in that. Okay, so remember this. If you want, you can note down this or take a screenshot also. Okay? So now after this, just a moment. So I will first erase all these things. Okay, so now here you can see, now the description is given for this method. So in the working stress method, design load is based on the uniqueness theorem. The design strength of material is based on lower bound theorem. Okay, so in this method, the serviceability is not considered. For such a low level loads, serviceability is not required. So in the, what is the difference? So if you see for the working stress method, in the working stress method, serviceability is not considered. Okay, so in the working stress method, what we design, we see the stresses in the material. In the working stress method, we always see what are the stresses in the materials, and we take care that the stresses in the material should not reach to the ultimate point. Okay, but we don't consider the serviceability. That serviceability we considered in limit state method. Okay, so the deflection, then your cracking, and all these things are there, those checks are there. We have already studied in DCS 1. In that we also take the check for development length and all these things. Okay, you have already done that. Those, all these things are comes under serviceability. It is considered in limit state method, but in the working stress method, what we do, we just consider the stresses in those materials, and we take care that those stresses should not reach to the what we can say maximum level. Okay, as the stress in the material increase, the size or the dimension of the members increase. This is the one more drawback of this working stress method, that if you calculate the sizes of any member by using the working stress method, then you will get the bigger sizes as compared to limit state method or ultimate load method. Okay, because we are considering the stress in the material in that case. Okay, but we don't consider the conditions in the serviceability. here in the working stress method. So working stress method म्हणजे simple जर तुम्हाला सांगायचं म्हणलं, if I tell you in the simple things for working stress method, what they do, suppose now 100 MPa is the stress, okay, then in the working stress method we design it round about to 150 MPa. This is our design. For this stress we design, if the maximum stress is 100, then we will design for 150. Okay, I am talking in terms of stress. Okay, so that in future also if the stresses get increased, it won't fail. But due to this increase, there will be increase in dimensions. Okay, due to this the dimensions will get increased, the dimensions of the member will get increased. Okay, so this is what happened in working stress method. Okay, so now the next point here, it is ultimate load method. Okay, ultimate load method. So in the ultimate load method, design load, it is calculated as, or it is known as ultimate load or collapse load. Okay, so here it can be calculated as working load into load factor, ultimate load. Okay, what is the working load? You multiply that by load factor. Here load factor is considered. In the working stress method we used to call it as a factor of safety. Here we and there we keep the factor of safety for the stress. We consider the stresses in the material. Here we keep the factor of safety for load, so it is called as the load factor. Okay, please understand the difference between this. So this is called as load factor, and this load factor is depend upon the load combinations. This load factor is depend upon the load combinations. You might have seen that while taking the different load combinations, sometimes we take 1.2, sometimes we take 1.5, these types of dead load plus live load. Sometimes we take dead load plus what we can say, instead of live load, sometimes earthquake load, or live load plus earthquake load. Different types of load combinations we take while designing any structure. Okay, so this load factor, this your load factor is depending upon your load combination. So these are nothing but your factors. Okay, these are nothing but your load factors, those which are depending upon your load combination. So here in the ultimate load method, what they have done, they are directly increasing the load. Okay, so suppose now the load is whatever x amount load is there, then what we do, we multiply that load by load factor. And how that value of load factor, from where we get that the value of that load factor, it depends upon the load combination, which load combination you are using. Depending upon that, the value of that factor is decided. Okay, and all these are the standard values which used over here, okay, in this load factor. Okay, so here the load factor is used. Then so now design stress, allowable stress, permissible stress, again it is calculated as the characteristic strength of the material divided by material safety factor. Okay, divided by material safety factor. So there what we do, there it is characteristic strength of material in working stress method I am talking about. In working stress method, what was given, it is characteristic strength of material divided by factor of safety. Okay, so here the characteristic strength of material divided by material safety factor. Okay, so material safety factor in beams, they are given over here, and normally we are going to use these factors over here. 1.5 for concrete, this we have already known, and 1.15 for the steel. Okay, 1.5 for the concrete and 1.15 for the steel, according to this ultimate load method. Okay, take down this. These are the important values. Again, MCQ questions or objective questions will be asked on this. Okay, objective questions, particularly they will tell you in the ultimate load method, what is the safety factor for steel, and some options will be given over there, and from those options you need to choose the correct option, that is 1.15 is your correct option. Okay, now moving further. So in ultimate load design method, okay, again in this method, again if you see in this method, serviceability is not considered. Okay, so that is why this method is not become popular. So in the working stress method and in the ultimate load method, the thing is that serviceability is not considered. Okay, after the application, once you design the load, once you analyze the load, then once you design the member, but after the application of the load on that member, some criteria should be there. What should be the deflection, what should be the cracking, what should be the width of the crack, what should be the ductility of the material, all those things which are comes under the serviceability. What should be the bond strength between the concrete and steel, okay, what is the limit for that, all these things are not considered in working stress method as well as in ultimate load method. But what is the difference in working stress method in ultimate load method? In working stress method we consider the stress, we take care that the stress in the material should not reach to the ultimate stress. Okay, ultimate stress ला stress नाही जायला पाहिजे. Okay, so the factor of safety for materials we applied over there. And in ultimate load method what we do, in ultimate load method, just 1 minute, just 1 minute. Okay, okay, so this is the ultimate load method. These are the key points I am telling you, as this is our first lecture, these are the key points. But when we are going to solve the objectives on these different methods, at that time we'll go again in deep in this. Okay, so what is exactly the meaning of the stresses in the material is considered, how those are considered, then if this is the thing, then why that method is not popular and why not it is used. Then in the same case, that ultimate load method, for the ultimate load method also the serviceability is not considered. So what is the difference between working stress method and ultimate load method, and then why ultimate load method is not used in these days, or why it is not popular. So all these things we are covered when we are taking the MCQs on that particular bit. Okay, now here today we will cover the overall what is the working stress, limit state, then ultimate load method, and then we will go through the procedure of different types of slabs, the design procedure. Okay, just we will go through this. So today we will cover only these two things, and then in the next lecture when we will move into the details of working stress method, then I will explain you one more time the detailed concept, and I will give you the questions and you have to solve those questions. Okay, in this way we are going to deal. So now in short, this is the ultimate load method. Okay, this is again it is not popular due to the serviceability is not considered. Yeah. And next the final, it is the limit state method. Okay, as you have already seen what is the limit state method, I will just give you the overview whatever written over here. The limit state is the condition just before the collapse. Okay, up to this condition member is safe to resist the external loads and also give proper service throughout its life. Okay, so limit state is the just a condition before the collapse. Okay. Up to this condition, so before collapse the member is safe to resist the external loads. Okay, so whatever the loads are coming on that member, it is safe and it can carry the load before the failure or before the collapse, and also it gives proper service throughout its life. Okay, so serviceability is considered over here in the limit state method. So the limit state method, it is divided into basically two types: limit state of collapse and limit state of serviceability. This is also we have seen. So limit state of collapse means in that flexure, shear, compression, torsion, it is again subdivided into these four types. Okay, flexure, so bending. So depending upon the flexure bending, we go for the design of beams. Okay, we have already designed the beams. Then shear, compression, as it is written over here, you can read the next word for shear. Beam is also there written. So sometimes while calculating the shear reinforcement in the beam, if you observe, we have provided the stirrups in the DCS1. Okay, while I have designing the beam, many of the times we have provided the stirrups in the beam. So why we provide the stirrups? Stirrups are provided to resist the shear. Okay, if you remember, I have told you at that time, we provide the stirrups where the shear force is maximum, the spacing between the stirrups, we reduce the spacing between the stirrups, so that the more number of stirrups will be accumulate in that area where the shear force is more. And as we move away from that area, we can increase the spacing between the stirrups. Okay, we can increase the spacing between the stirrups. So if I draw the diagram, okay, so if I draw the diagram, so suppose now this is the beam and these are the supports. These are the supports. So you know that at support the shear force is maximum. At the support the shear force is maximum. So what we will do, we will provide the stirrups at a lesser distance over here. The distance between the stirrups is less up to the certain length. So it may be L by 5, L by 4, L by 4 to L by 6, that we will choose. But standard on site in practice, now the contractor, builders or engineers, what they do, up to the length of L by 5. These stirrups are closely spaced. Okay, from this side also where the support is given, at that point these stirrups are closely spaced. Here these are the closely spaced stirrups. Okay, and as we move towards the center, so here the shear force is less, so we can increase the spacing between the stirrups. Here you can see the spacing between the stirrups is increased. Okay, the spacing between the stirrups is increased. Normally on the site the thumb rule is that for this region, so this is this point, this is your normally, just 1 minute here. Okay, so for this is your L by 5, this is also L by 5. So for this region normally your spacing is 100 mm center to center for stirrups. Okay, 100 mm म्हणजे किती झालं 100 mm म्हणजे in on site that engineers or um, all the everybody the labor they speak in inches and feet. So normally they keep the spacing for 4 inches. Okay, 4 inches means what, 100 mm. Okay, 100 mm. And as we move towards the center, if the shear force is very less, then we can go up to 300 mm. I am saying up to 300 mm center to center. Okay, up to 300 mm center to center. So what, so basically what does it implement, what is the benefit of providing this? So where this in this area the shear force is maximum, we are providing more number of stirrups, and here the shear force is less, so we are providing less number of stirrups. Okay, तर तुम्ही हेच spacing continue ठेवला इथं. If you provided the same spacing whatever you have provided here in the L by 5 region, if you continued the same spacing throughout the beam, then also the beam is safe, but it is over safe and it will become uneconomical. Unnecessarily you are providing the more steel in the beam. Okay, so that is also not good. So that is why for shear we have seen this. That is why once this word comes shear, I am trying to recall you the things. Okay, so in this way, for the support, the stirrups are maximum, the closely spaced, and at the center it is the spacing between the stirrups is increased. Okay, the next is this compression. Compression, you know that column, we have designed the column. Okay, Columns can be designed for axial loads as well as eccentric loads. Okay. In the case of column, that also we have seen, if you remember. Suppose now this is the column. So what is the meaning of column first? You know that a member which carries a load along its length is called as column. And what is the beam? A member which carries a load perpendicular to its length. It is normally called as beam. And if the load is along its length, that is along the axis or away from the axis, whatever may be the thing, but it should be in the line of that axis. Okay. So here, if I draw the axis, these are the axes of the columns. Now, what actually loaded columns and eccentrically loaded columns, those we have already seen. Still, I will draw over here. If the load is acting exactly along the axis, okay, then it is called as axially loaded column. This is your P. This is nothing but this is your axially loaded column. Okay, and if the load is eccentric means what? Now suppose the load is acting at some distance over here, P, same load P, but now it is not acting exactly on the axis, so there will be the eccentricity E. Okay, this is the eccentricity E, and this is called as eccentrically loaded column. Okay, so how do we calculate the compressive stress in this case? It is P by A. Here it will be axial compression will be there. Okay, and here in this case, if it is eccentrically loaded, then it is P by A plus minus M by Z. So M by Z is nothing but it is for bending stress. So here axial compression is there, so axial compressive stress is there as well as bending stress will be there. In the case of eccentrically loaded columns, we have seen this. Okay, so if you further simplify this, it will be P by A plus minus M is nothing but P into E by Z. Okay, and Z also you can again write I by Y, so it is PEY by I. This can also you can write in this way also, or you can simplify this further. This plus minus sign, it depends upon the, what we can say, nature of your bending. Okay, so these are the things. Then the last one is the torsion. In the case of L beam, torsion will be there as it is in the corner. We have all T beam, L beam, then beam curved in plan. Okay, so this portion, this beam curved in plan, this is for MTech. Right now you have not seen this. Okay, L beam design. L beam design, I think we have seen that T beam design, L beam design. Okay, so this comes under, all these things comes under the limit state of collapse. All these things comes under the limit state of collapse. The next is the limit state of serviceability. So if you want to draw this, or shall I clear? करू दे का क्लिअर झाले का लिहून? Anybody? Okay. So I hope now you have taken the notes. Okay. So next we will come to this limit state of serviceability. Okay. So what is the limit state of serviceability? If you see, it is again divided into sub points. That is the deflection, cracking, vibration, fire resistance, then ductility, durability, and ductility also comes under over here. Durability. So if the material is having, it is having more ductility, then automatically its durability also increase. Okay, I hope now you know the meaning of all these things. Deflection, you know that we have we take the check for deflection. In case of slab, if you remember, while designing we take the check for deflection. We always assume the depth of the beam. Okay, for continuous beam it is L by 10, or we calculate the depth of beam based on, we equate the bending moment to moment of resistance. Right now I'm talking about this deflection. Okay, so I will repeat once again if you not able to correlate this. Deflection. See, while designing by limit state method, we have already studied in DCS 1. Okay, while designing with this limit state method, while designing the slab, you may remember that we have taken the check for deflection. Okay, and whatever the depth of the slab we take now, that span by 20 into modification factor that we do as per IS 456 2000. Okay, so this is the span by 20, this value. From where this value comes? This value comes from this deflection criteria. Okay, it is not just the thing that IS code is it is given in the IS code, that is why we are using, that is the true, it is given in the IS code, that is why we are using, but still this span by 20 and all these things, where from these comes? So this comes from these deflections. Okay, so by considering the deflection, we, so this is your formula for D, depth of the beam. So while considering, by considering the deflection, we take the depth of the member in such a way that it should not deflect. It should not deflect to more than permissible value. Okay, so now it is open. Okay, so what was I was talking? I think I was talking about this deflection. Okay, so we were talking about this deflection. So that is the thing, that we always use the formula depth is equal to what? Span upon something. Okay, span upon maybe some constant is there, 20, 30, 26, 23. Modification factor is also there. Okay, this is taken by considering this deflection criteria. Okay, next is the cracking. So, if you observe now in our day-to-day life, in the this our while after concreting, you may observe that if a new construction is also there, suppose it is residential, commercial, whatever it may be, you many of times you observe that कधी जाता येताना बघा दिसलं तर, even though the construction is new, okay, even though the construction is new, 1 minute. Okay, so cracking, if you can observe, if on new construction is also there now, you can see the cracks are there in the wall. Okay, अजून plastering चालू आहे, and in that also you can find sometimes that there is a cracking. Okay, so why it is happening? Okay, so when you make a mix of the cement with that sand, coarse aggregate, fine aggregate, and you prepare the concrete. After the preparation of the concrete, when that concrete is used for the casting now, after the casting and curing, you have to apply some DPC coat on that. Okay, if the person, engineer or that contractor, if they don't apply that coat on that, then what will happen? Due to the inside reaction of that concrete, there will be the evaluation of the CO. Okay, you know that the chemical composition in the concrete. Okay, and due to which there will be cracking on the walls. Okay, so nowadays on TV also you may see that much more ads are there of DPC, damp proofing course and all this. So that is why that DPC is very important in that case. So the this cracking. Okay, so nowadays that cracking can be avoided by using these what we can say adhesive materials or admixtures. Those are adding in the concrete. Then vibrators, you know that vibrators, needle vibrator. Then for the large structures, for compaction is not done. It is done by vibrations also, and vibration loads also there. Suppose now a long bridge is there, and on that bridge, now suppose the truck is moving and that truck is having 30 tires. Okay, so in that case it is a moving load, no doubt in that, but some vibrational load is also acting on that structure. Okay, that also it is comes under this limit state of serviceability. Okay, fire resistance. You may surprised to know that there is a diploma in fire engineering. Okay, जर तुम्ही ऐकलं असेल तर in fire engineering you can do the diploma. So that much of vast is this fire engineering and fire resistance. How to make the building fire resistance and what are the safety measures and all those things. Okay, so this also comes under this serviceability criteria. And finally is durability. How the durability increases once your concrete is of proper mix, it is casted well, it is well cured. Okay, when the steel provide in that, it is the ductile. If you have kept the sufficient space for the steel for expansion and contract in summer, it will get a little bit there will be a little bit expansion in that steel. In winter there will be a little bit of contraction due to the variation in the temperature. You know that what is the temperature stresses, that is alpha TL. Okay, you have already studied this, so I will not go into the detail of that. So once you do all these things very correctly now, then ultimately its durability is increased. Okay, if you fail while doing these things or while casting or constructing a structure, if these things are not done properly, then it hampers on its durability. So this durability consideration is also comes under the this serviceability. Okay, so while taking the objectives, then again we will go into the detail of this, and that time much more details we will take. Okay, so for the time being, you just I am rebrushing you what are the things and what we are going to learn. Okay, so collapse, then serviceability, and after that these things also we have studied: design load, ultimate load, factored load, collapse load, limiting load, all the things are same. So design load, it is calculated as the characteristics load into gamma f. Gamma f is the partial safety factor. Okay, gamma f is the partial safety factor. So we use the partial safety factor for designing the loads, and here you can see the partial gamma f is the partial safety factor for forces and loads. It is given in IS 875 page 5. This also you should remember. Okay, this also they can ask you and you will get confused from most of the times the student give the answer, it is taken from the value of gamma f is taken from IS 456 2000. It is wrong. The value of gamma f, that is your partial safety factor, it is not given in IS 456 2000. It is taken by taking the reference from IS 875. Okay, there that value is given. Then the next thing comes is this characteristics load. Okay, this also you already know what is the characteristics load. The load which has 95% probability of not being exceeded in the life of the structure is the characteristics load. So the load which is having 95% probability. Okay, so suppose now if you design a beam and suppose 150 kilonewton is the you have taken the characteristics load 150 kilonewton. Okay, so what is the meaning of that 150 kilonewton? So the 95% probability is that this when the actual load is applied and the structure is constructed, the load will not go beyond that 150 kilonewton. Okay, and what is the probability of that? It is 95% probability. That type of load is called as the characteristics load. Okay, so these are some things, these we will see later on, these formulas and all these things which are given further. Now we will move to our slab. Okay, and now I will quickly go through the design of slabs, what which we have already done. So we will see the different types of designs of the slab. Okay, so I will go to that PPT. This is the slab design. We will see the procedure. Okay, now why I am revising you all these things, because in the next lecture we are going to take it in detail, and I am going to ask you the questions. I will give you the questions related to GATE, MCQ, UPSC on this. Okay, so that is why I am revising these things, so that you can recall, and today and tomorrow before our next lecture you come with the preparation. Okay, that is why I am taking all these things once again. Okay, so here you can see the design of one-way slab. So what is the numerical here? Design a simply supported slab, supports on a masonry wall having dimensions 3 meter by 6.5 meter. So what is the dimension? It is 3 meter. The dimensions are 3 meter by 6.5 meter. These are the dimensions of the panel. The slab carries a live load of 4000 Newton per meter square. So 4000 Newton per meter square means 4 kilonewton per meter square. It is 4 kilonewton per meter square. Use M20 NFE 415. So you have to use M20 NFE 415. So what we will do in the design of one-way column. So here, sorry, one-way slab. So here, first of all, we don't know it is one-way or two-way. Okay. So first we take the check that which type of slab it is. So here what we have done, also in the given numerical, what is the width of support? Here they told us that it is supported, but what is the width of support? It is not given. So here the width of support, it is assumed as 120 mm. You can assume 230 mm also. Whatever the supports is there on the site which will be there for the slab, that value you can take over here. Okay. So now Ly by Lx. Ly by Lx is equal to what? Ly is 6.5, Lx is 3. So here you can see 6.5 and 3. 6.5 and 3. So that ratio is 2.16. So your Ly by Lx ratio is greater than 2. So this is the one-way slab. Okay, and at that time also we have seen it is given in Annexure D 1.11 page number 90. Okay, these are my handwritten notes. If you want, you can take the screenshot of this, because everything in detail it is given over here. Okay, these notes will be helpful to you after your BE also. This is helpful to you. Okay, you if you want, you can take this. So one way slab, annexure D आणि कुठं दिले ते, so it is given in D 1.11 page number 90. Okay, so for slabs, percentage of steel 0.3 to 0.4%. So generally it is thumb rule. Now this is not a compulsory rule. Huh? Again I am going to tell you, it is not given in any IS code, it is not given anywhere. But normally after designing of so many structures, some thumb rules are there in this our construction industry, and this is one of the thumb rule. For slab now, normally the percentage of steel varies from 0.2% to 0.4%. Okay. For slab, percentage of steel normally it is taken from 0.2% to 0.4%. Okay. Now, so in between these values 0.2% to 0.4%, you can consider the percentage of steel. So here the 0.3% of steel is assumed, 0.33% of steel is assumed, and this Fs is equal to, it is 0.58 Fy. Okay, stress, this formula it is given in the IS code on page number 38. Actually, how does it come? You know that actually in the IS code it is given as Fs is equal to 0.58 Fy into AST required divided by AST provided. In this way it is given. So what we assume? We assume that whatever the steel required, that steel we are going to provide. Whatever is the required steel, that we are going to provide, that we assume initially, and that is why this ratio becomes 1. Barabar hai na? Suppose now the requirement of the steel is of 100 mm square. So we are going to provide 100 mm square. That is our assumption. Whatever required we are going to provide. Actually in practice we are provide more than required. Actually we design in such a way that whatever required we provide more than that. But optimum thing is that whatever required we are going to provide. That is why it is 1. So here you can see Fs is equal to 158 Fy. It is 240.7. So it is nearly equal to 240. This is the line on the graph. So we have to see the line which is having the strength 240. So now MF is equal to what? It is 1.4. Okay, हे कुठून आलं MF? This is from graph, and that graph is given on page number 38, IS 456 2000. तिथून ही value आली. From there you have taken this value. Okay. Now after this we have used the formula for effective depth. So D is equal to, what is the formula? D is equal to span divided by 20 into modification factor. So again this span by 20, from where does it come? It comes by considering the deflection. Okay, deflection, that is, this is what I am trying to tell you. So D is equal to span divided by 20 into modification factor. This comes from this clause. Clause is specified over here on page number 36. If you put all the values, then you will get the depth. So this is small d, that is the effective depth. Okay. So here also I have written the one note. One way slab always consider shorter span. Okay. And so shorter span we considered everywhere while designing in two-way also. So D is equal to 111.42 mm. Now we have assumed the clear cover of 15 mm. For slab, normally 15 mm clear cover is assumed. 15 mm clear cover, and bar diameter 10 mm. Okay, so our bar diameter is 10 mm. So capital D, overall depth. So it is the effective depth plus 15. 15 is the clear cover, and plus 10 by 2, half of the bar diameter. Okay, so this is your overall depth. So overall depth, this is the overall depth 135, and from this rounded overall depth again we have calculated the effective depth because it comes out 131.42. So we have round up that overall depth to 135. So if we increase our overall depth, then our effective depth is also going to increase. So that increased value we are find out by doing the reverse calculation, opposite calculation of this. So D is equal to, again from overall depth, if you minus clear cover and bar diameter, half of bar diameter, you will get small d. Small d is nothing but your effective depth. Small d is nothing but your effective depth. After that, effective span. Okay. So after that, effective span. So what does IS code says? It is given in the criteria clause number, page number also it is given. IS code says that center to center of support. This is the first condition. Second condition, clear span plus effective depth. This is the second condition. What is the clear span and effective depth? Whichever is less. Whichever is less. That you should consider. Okay. So now after this, so somebody has asked me the question, what is Fs? So open your IS code, go to page number 38. There is a graph is given. The formula is there for Fs, and what is the meaning of Fs, that is also given over here. Okay, in DCS I think many times I have taken. You study that. If you won't understand, then I will tell you. So here you can see L effective is, what is that, clear span plus effective depth. So it is calculated by both the criteria, and whichever value is less, that value is taken over here. Okay. So now after this we do the load calculation. After the effective span we always do the load calculation. So in the load calculation, first is the dead load of slab. First the dead load of the slab is calculated, that is self weight. It is, we assume over here the 1 meter width of the slab. Okay, 1 meter width of the slab we always assume. So you can assume at the start so that you will get all the values in kilonewton per meter. Otherwise, after calculating all the loads also you can assume 1 meter wide strip. Okay, here I have assumed after calculating all the loads I have taken the 1 meter wide strip. But while teaching the DCS one, what we do, we see at that time I have taught you like this. Initially you can assume 1 meter width of the slab, so that here itself you will get the value. This is the depth of the slab, your overall depth 0.135 into 1 into 25. So this, instead of this kilonewton per meter square, you will get the answer in kilonewton per meter. That is also correct, there is no problem. Okay, or otherwise whatever I have done over here in my notes, that way also you can evaluate the total load. So everything will be in kilonewton per meter square, and at the end you can assume 1 meter wide strip of the slab, and then you can multiply this quantity by 1, so you will get the answer in kilonewton per meter. Why we want it in kilonewton per meter? Because the kilonewton per meter square is the unit of stress, it is not the unit of load. Okay, and whatever our formulas are there to calculate the bending moment and to calculate the shear force, those are for the loads, those are not for the stress. From stress you cannot evaluate the bending moment or shear force. Okay, so that is why we want it in kilonewton per meter, so that we can evaluate the things further. So now here you can see after this 12.56 kilonewton per meter, here it is, you can see the self weight of the slab, it is calculated. Then floor finish, it is assumed. Then live load on the slab, this is given in the numerical. So total load it is calculated. After that the ultimate load is calculated. Okay, and then 1 meter wide strip considered, and we got this load in kilonewton per meter. So after the calculation of the load, and now effective length is also known to us, effective span is also known to us, and load is also known to us. So from that we can calculate the bending moment. So bending moment is WL square by 8, which is equal to this WL square divided by 8. So this is your bending moment, whatever you have calculated. And now once you equate this bending moment to moment of resistance, then you will be able to calculate the required depth of the slab. Okay, then you will get the required depth of the slab. So what is the depth actually required? So here in this case you can see after equating mu to mr, so this is your mu. Mr, you know the formula, here I have written 250 for 415 500. What is the coefficient? 0.419, 0.138, 0.133. So accordingly you have to choose the coefficient. FCK BD square is the same. So B, it is 1000 mm, as we have assumed 1 meter wide strip. So from that you get the value of this D, and it is safe because we have provided 115 and the required is 75. Okay. So further calculations, you know that AST, this is the formula of AST. In this formula, if you put the values, you will get the AST. Now you know the bar diameter. So from that you can calculate the number of bars. Okay, from this you can calculate the number of bars. Okay, total area of steel divided by area of the single bar. So from this you have got the number of bars, you round up those bars. So if once you round up those bars, now 5 bars are required and you have round up to 6 bars. So you have increased the area of the steel. Correct, because 5.03 bars it is impossible to provide. That is why what we do, we round up the bar. Okay, and after the roundup, previous slide. Okay, so this is the previous slide. Any doubt, any difficulty? Any doubt, or shall we move further? Okay, okay. So now once we come forward further, so now here, this all we have done. Just I am recalling the things. So number of bars, total area of steel divided by area of single bar 5.03. It is impossible to provide in that way. So we provide 6 numbers. And once we increase the area of steel, we have to calculate what is the increased area of steel. So that is why we have calculated AST provided. So 6 bars of 10 mm diameter, this is the AST provided. Okay. Then the spacing of bars. So how do we provide the spacing of the bars for main steel? It is as per the clause number 26.3.3, page number 46. Okay. So lesser of following three. The lesser quantity from these three we need to provide. So spacing is equal to, it is area of single bar divided by total AST into 1000. So this is the spacing. So we have round up the spacing to 165. Always we reduce the spacing. What is the logic behind reducing the spacing? If you increase the spacing to the higher value, then your number of bars will get reduced. So we reduce the spacing to the round up value so that number of bars will get increased, which will add more safety to our structure. The spacing is 3D, so 3 into effective depth. This much is the value, and lastly this is the value. So 165 it is provided for the main steel. Now it comes distribution steel. So after the main steel here, percentage of steel. What is actually provided? It is 0.4%. Okay. 100 AST upon BD. AST it is known to you. B is known to you. D is known to you. Now distribution steel. ASTD. 0.12% of gross area. It is given on page number 48. This is the clause number. 0.12 by 100 into B into D. So if you put these values, you will get the answer. You will get the number of bars. After the number of bars, you can calculate the distribution steel provided. Then spacing of bars. Again, you will see this in page number 46. 26.3.3b. Here it is 26.3.346. But here there is a sub clause in that B for the spacing of distribution steel. And here from this formula again you will get, instead of 3D the change is here 5D, instead of 300 the change is here 450. Okay, first spacing calculation will remain same, that is the values will get changed but the formula is same. So by solving this you will get the number of bars distribution steel. And after that, check for shear. So three checks we take to check for shear, check for deflection, and check for development length. Okay. So for the check for shear, here the SF at the support VU is WL by 2. You know the formula. If the simply supported beam is there, then the reaction at its end, the reaction at its end will be WL by 2. So just put the formulas, you will get the shear force, then calculate the tau V nominal shear stress. And that nominal shear stress, how it is calculated? Stress is equal to load upon area, or you can say shear force divided by area. So the shear force, it is already known to you, 19.56. This is the force divided by area is B into D. B is 1000, D is 115. So you will get the shear stress. So this is the clause number. From this clause, we have calculated the permissible shear stress. Okay. So the here shear strength of the concrete, tau C dash. What is the shear strength? It is 0.32 Newton per mm square. So 0.32 Newton per mm square कुठून आली? तर हे percentage of steel, and by using the table given in the IS code on page number 72, there is table for different grades of concrete. Permissible stresses are given. Okay, from that table this value is calculated, and after that, once your permissible stress is more than your nominal stress, that is your tau c is greater than tau e, then it is safe. Or you can say that tau e is less than tau c, then it is safe in shear. This is the thing. Now next is the check for deflection. So percentage of steel provided is 0.4%. So again the same things are calculated. Fs is equal to 0.58 Fy. This is AST required and this is AST provided. So this time this value of Fs is 190. From that again modification factor is calculated, and D required for deflection, it is calculated 94.54, which is 95 mm. So for the fulfill the deflection criteria, your depth should be 95 mm, but you have provided 115 mm. So D provided is greater than D for deflection, hence it is safe. So this is the check for deflection, and then after that check for development length. So this check for development length, it is taken as, this is the formula, development length is equal to 5 sigma s upon 4 tau bd. This is the formula, and it is used from this clause number 26.2.1, page number 42. So, and this development length, it is calculated as phi, as it is sigma s. Sigma s is nothing but it is 0.87 Fy. Sigma s is nothing but 0.87 Fy. That value is put over here. Then 4 tau bd. So the value of tau bd is 1.2. This value of tau bd is 1.2, and this 1.6 is the 60% increase for torch steel. Okay. So if torch steel is used, Fe415, Fe500, then the 60% increase will be there. And that too, if the torch steel is provided in the compression zone, then you need to further multiply this by 1.25. So you have to further increase it by 25%. So right now the only torch steel is provided, and it is provided at bottom of the slab. So we have to increase this by 1.6%. That is 60%. We need to increase this. So multiply by 1.6. This is the development length. In what we can say MCQ objective questions, this can be asked. After using the torch steel, development length is increased by dash dash percent. How much percent? Okay. And if the torch steel is provided in the compression zone, so the development length should be increased by how much percent? That also can be asked. So remember these things. And now, as per usual procedure, by referring this page number 44, we have calculated the deflection check for development length. Okay, so it is 1.3 m1 VU plus L0, and from that we have calculated this. So ultimately this m1 it can be calculated as mu by 2. So this is the value. VU also calculated by same, already we have calculated the value. And then L0. L0, here I have shown the diagram. What is the exactly meaning of L0? So L0 is the this much of distance. If you see this much of distance. हे कुठून घेतलेलं आहे तर this is the center of support. This line, this vertical line, it is nothing but center of support, and this line, this whatever I have shown over here, this is the clear cover, 15 mm clear cover. So from the center of support, if you minus this clear cover, then you will get this L0. Okay, so this is the L0 length. So how can we calculate this? So if your support length is 120, and now if I want to calculate this L0, so the axis of the support will be at the center. So at the center means half of this 120. So it is 120 by 2, and if you minus this clear cover from left hand side, so what will remain? 120 by 2 minus this 15. So it is 60 minus 15. So it will be 45. So in this way this L0 is calculated. So here in this diagram it will be clear to you what is the distance L0 from where to where it is measured. Okay, so finally we will come to the final this stage. So here you can see this is your L0, this length. You can clearly see where the L0 is given over here. This length is L0 from this point to this point. This is your L0. ज्यांना DCS 1 मध्ये समजलं नसेल त्यांनी बघून घ्या. This is your L0 length from the center of support to the clear span पर्यंत, आपलं clear cover पर्यंत. This length is L0. That is why we are using this formula to calculate the L0. Okay, and after the taking this check, finally what we do, we draw the diagram. This is your reinforcement diagram. This we have already drawn. So now I am not going into the details of this. Okay, so in this way we design the slab. So this is the, what I can say, a small rebrush to all of you, that I want to take some revision for this also, so that now for the coming to, before coming to the next lecture, next slab also, now you do it at your own, at your home. The next slab which I have already taught you, two-way slab, then continuous slab, cantilever slab, that procedure you should see. And then basic of limit state method, that we have also learned, that basic also you should see today. And in the next lecture we will take all these three methods in detail, and then question answering session. Okay, so I think for today it is sufficient.